हरि करना।
Now it's time to look into the transformation of random variables. In probability theory, transforming a random variable RV involves applying a function to the RV to obtain a new RV. So that's what we call it as a transformation. So transforming a random variable involves applying a function to the RV to obtain a new RV. So this process is important in many areas of statistics and machine learning, including computer vision and NLP, natural language processing. So suppose y is equals to f of capital X is a random variable, and the function, if we elaborate the function, it is equals to ax plus b, be a linear function of a vector valued random variable capital X, and A is a matrix and B is a vector. So both are constants. Okay, both are A and B are constant, but one is vector constant, other one is matrix. Okay, so this is what the function we have. Ax plus b, ax plus b, in that capital X is a vector valued random variable, okay. Now, suppose E of X, expectation of capital X is equals to mu. Okay, not the expectation of the function. It's expectation of the capital X. Only expectation of the random variable is mu. And covariance of X. Okay, only X, covariance of X is equal to sigma. Then for the vector valued random variable Y is this. So E of, obviously, what is f of X? What is f of X? F of X is equals to ax plus b. Then if you want E of Y is nothing but E of f of X. So E of f of X is nothing but E of ax plus b. So then you can replace this can be converted as a and b are constants, then it's a times e of x plus b, because we have seen the properties of random variables. When you multiply with the real value, so then you can use it if in scaling up random variable property. So this can be converted into the a times e of x plus b. But what is e of x for us? It's e of x is equals to mu. So a mu plus b. So that's how this is what we call it as a transformation. So covariance, for similarly, covariance of y is equals to covariance of ax plus b, and then a times sigma a transpose. So likewise, if y is equals to f of x, a transpose x plus b, this is a different function. A transpose x plus b be a linear function of a vector valued random variable capital X, and a is a vector and b is a scalar. But this time b is a scalar. There b also a vector and a is a matrix. So that's the reason it has become A transpose. But here A is a vector and B is a scalar, both constants. Now suppose E of X is equals to mu, same covariance of X is equals to sigma. Then for the scalar valued random variable Y, E of Y, that's estimation of expectation of Y. So expectation of Y is equal to expectation of expectation of A transpose, because that's what the function we have. Expectation of A transpose capital X, a random variable, plus B, and then again A transpose times E of X plus B. So A transpose mu plus B, and but the covariance is slightly changes. Covariance, sorry, this time it's variance. To calculate the variance of Y, it's variance of A transpose X plus this. Okay, let's take one example here. So this is a transforming a random variable. Random variable. Transforming a random variable involves applying a function to the RV to obtain a new RV. So let's take the first example. Example one. Suppose we have an random variable RV x presenting a same example. Let's take x presenting brightness value of a pixel in an image, x presenting brightness value of an image brightness value of an pixel in an image, and y represents and then x okay, we got the x value, so we don't need to worry about the y here because we just want to calculate the transforming of this. So uh, this is what then we can transform x by applying a non-linear function such as the sigmoid function. Let's take a sigmoid function to transform it. The now new RV. So y is equals to sigmoid function of x. So this can be calculated. So now new RV, let's take it as a new RV. The new random variable will represent as a y. So y is equals to new random variable. So then y is equal to 1 divided by, obviously you know what is sigmoid function. It's very simple, 1 plus exponentiation of minus x, power of minus x. That's what is your sigmoid function, and this is what the new RV, a new random variable after transforming using a sigmoid function. This transformation maps x to the range 0, 1, which can be useful in some image processing tasks such as constant enhancement and thresholding. I'll write it down here. So application of use doing this transformation is image processing tasks such as image processing tasks such as uh, uh, contrast contrast enhancement, and thresholding threshold thresholding. And then the next one, second example 2. Suppose we have an RV random variable x representing the length of a sentence in words. X represents length of the sentence in a word, length of sentence in words. So we can transform x by applying a logarithmic function to obtain a new RV. So y is equals to new random variable, then y is equals to logarithmic function of x. That's it. So this transformation can be useful in some natural language processing tasks such as application can be used some natural language processing tasks such as text summarization text summarization and topic modeling, where the length of a sentence may be less important than the content of the words. So transforming random variables Transforming random variables can also be useful in statistical modeling, where we may want to apply a linear regression model or other machine learning algorithms that assumes normality or other distributional assumptions. By transforming the random variables, we can often achieve a better fit to the underlying distribution and improve performance of the model. So, in summary, transforming random variables is an important tool in probability theory, statistics, and machine learning. By applying mathematical functions to random variables, we can often obtain a new random variables that have more desirable properties for specific applications in CV, NLP, and other fields.